Hello, everybody. I'm Lars Wimberg, and I will take you through this presentation about the key to eVTOL success when it comes to noise and environmental issues. So first, a bit about myself. I'm Lars, as I told you before, and I've been working here at the company for almost 10 years. I'm focusing on aerospace and defense applications, and I would like to give you some more insights in how to actually uh, measure noise from drones and eVTOLs and give you some examples on how this is actually implemented in the real world. So the presentation will be roughly 3/4 of an hour, and there will be space for answering some questions afterwards. And you are always welcome to send your questions in the chat, and I'll take a couple of them in the end. And then if we receive more questions, I'll try to answer them in mails afterwards. So if you have anything, don't hesitate to just write it in the chat and we'll come back to you. So this topic, it is about eVTOL and noise from these vehicles. And first of all, I would like to just give you some background. The eVTOL technology, it has been evolving over time, and now seems to be the time where it's going to really be mature enough to be introduced in different countries and in different services. There is, though, some problems still, and one of the issues, it is the noise pollution. And you'll find out after this presentation here that there are a little bit lack in standardization in this area, and therefore it is very difficult for the industry to come out with some equipment that will be able to work in all different countries. And of course, when talking about noise from flying vehicles, it is also an issue about public perception and community acceptance. So if it is not having any public acceptance, then it will be difficult to actually introduce it in different areas. There will be resistance from people living close to the areas where they are operating, and so on and so forth. So first of all, why is it important to measure the noise from airborne vehicle? It is for different reasons and for a lot of different reasons. There could be some legislations and so on, but I would like to bring up that the uniformity and consistency is the primary reason. And the reason why I'm saying that, it is that only by having a uniform and consistent standardization in the global world, it is the only way forward to make international and global systems that can work in different countries. And this is definitely crucial for a global industry and the research to have some common rules to adhere to. So you can compare this a bit with the commercial flights. We have a regime in the ICAO talking about the certification stages, stage 1 to stage 5. That is described in the ICAO Annex 16, and I will be back to that later on in this presentation. And we also have legal requirements when it comes to airports, how they are operating, what is the environmental capacity for different airports. And that is described in different standards. One of them is the ISO standard 20906 at 2009. Okay, so maybe you're saying that it's quite easy. I mean, everything is the same. It is noise coming from the sky, from the air. So, of course, if we know how to measure the noise from one object in the sky, we can just adopt that to everything else and everything will be fine. However, it's not that simple. if we are talking about aircraft types or vehicles in the air, there are different vehicles and they have different noise characteristics. So if you take a subsonic jet airplane, has totally different parameters than a helicopter and a lightweight, a small multi-rotor unmanned aircraft system. So different equipment requires different ways of doing measurements. And I'll come into the details quite soon on this. But first of all, maybe just characterize the different noise sources, what they're actually looking like. And if we take a subsonic jet airplane, then first of all, the distance between the noise source and the receiver is pretty long. So that means that people are living, of course, some of them are living close to the airport, but in general, there are pretty long distance between the noise source and the receiver. It is also a very fast moving source, and it has a frequency content which is lower than 10 kilohertz, and that it goes together with the distance between the noise source and the receiver. Because of course, if you have a higher frequency than 10 kilohertz, they are basically filtered away due to the distance from the noise source. And then it has a limited tonal content when you take below 10 kilohertz. If we go to the other or to the next one, that is a propeller-driven aircraft. Then the distance between the noise source and the receiver is medium, because of course you are in a smaller airport, you live closer to the airport, and therefore it is a closer distance between the aircraft and the listener. That goes also with the altitude it is flying on, and therefore it is a different source. Then it is also a slower moving source, and it has a frequency of below 10 kilohertz also, but it is also including some tonal content. If we go to the third class that I have on my presentation here, it is the lightweight and small multi-rotor UAS. First of all, the distance between the noise source and the receiver is short, because if you are considering, for example, a parcel delivery, you might deliver the parcel in populated areas, which means that the distance will be shorter than for a commercial jet airplane. It is also a stationary source. It could actually be hovering just over your head, and therefore it is a stationary source in some cases. And the frequency, because the closer proximity of your ears, it is that it could actually involve also higher frequency than 10 kilohertz. And it has a tonal content. So as you see, different sources are having different characteristics, and therefore it is also important to develop standards that can actually cope with different noise sources in the air. So I'll go to the next slide here. Do we already have some legislation? Yes, I have been into a couple of them, and I'll not go through all of them right here, but I'll just show you some of the regulations or standards. If you take this first one, the lowest one, the ISO 20906, this is unattended monitoring of aircraft sound in the vicinity of airports. So this is what we usually call airport noise monitoring systems. If we take the second one from the lower part here, evaluation method of noise certification of propeller-driven airplane not exceeding 8,618 kilograms. This is the ICAO Annex 16, and this is the certification standard for how you're actually certificating the aircraft in this class. And that goes for the next one as well. The third lowest, this is also ICAO Annex 16, and this is for subsonic jet airplanes. So there are already a lot of standardization, and you might say that, well, maybe we can just find one that can fit into the drone or eVTOL market. And unfortunately, that has turned out to be not the case. it has some content that are different from other sources, and therefore we need to develop new standards for this area. So having said that, first of all, taking a look at the microphone position in the different standards. So if we take the ISO airport noise monitoring standard I talked about, these are microphones that are, according to the standard, mounted 6 to 10 meters above the surface. And then we have the ECAO. This is for the certification. They are located 1.2 meter above the surface. And then we do have also what we call ground board microphones. And this is the second ECAO, the propeller-driven airplanes. And that is defined as an upside-down configuration. And then we have probably the latest in this scheme of legislations. This is the ISO standard for drone monitoring, or for smaller unattended vehicles. It has also an integrated configuration. And I would like to come a little bit more in detail into the 4 different solutions here. Because when you understand that, you also understand the necessity of having different methods. So first of all, the first 2 ones here, these are microphone over a reflected plane, and these are mounted on poles. So if you take the first 2, that was 6 to 10 meters, and then it was 1.2. And there you actually have a minimum ground interference. And the reason why they're mounted in that high position, it is of course that you would not have that much interference from the ground. You don't have that much reflections from the ground, and therefore this is more like a free field measurement. If you take the ECAO method, for jet airplanes, these are dictated to be 1.2 meter above the ground, and these are having some ground interference. You will have some reflections from the ground going into the microphone here and creating some problems. If you take the other 2 methods here, it is in the ground board microphones. You have this for propeller-driven airplanes. You don't have any ground interference with them, because you have an effect where you are putting the microphone very close to the plate. And I will come into the technicalities of this further on in the presentation. But there you will have the interference from the microphone position in itself, because you will have some disturbances because of the microphone mounted in an upside-down configuration. And then you also have this integrated model where you're integrating the microphone into the ground board. There you don't have any ground interface, and you don't have any interface from the microphone position. But I will come into all that just in a second. So the first one, that is the ISO 20906 from 2009. You'll find out that the reason why these are mounted on a 6 to 10 meters height from the ground, it is to avoid the ground reflection. And this is quite good, because then you are coming very close to a free field condition. Unfortunately, this method, it's more based on fixed installation, where you're mounting the microphones, you're leaving them there for 6 years, for 10 years to do permanent monitoring. And therefore it is quite expensive and unpractical, the installation of mounting 10 meters mast around the airport. But if you have the same position over the years, that is making a good sense, because you are avoiding a number of issues. For a certification purpose, that is just one test, and therefore it is not making that much sense to put it in a fixed position 6 to 10 meters above the ground. So this is the second method. This is the evaluation or a certification test, and this is for the subsonic jet airplanes. You will have a microphone that is mounted 1.2 meters above the ground, and there you will have some interference from the ground. So you will see it here on the schematic picture. You have a sound source here, you will have a reflected wave, and you have a direct wave. So that means that you will actually have two different noise sources hitting the microphone. And when it comes to a non-stationary noise source, that might not be a big difference or a big issue, and I will show you that. But if you would have a hovering condition, a hovering helicopter or a drone, for example, that could make a big difference. If you have a reflected wave that is equally big than the direct wave, and it is just in 180 degrees phase shift, that would even out the result. So this is only good if you have a distance between the noise source and the receiver that is fairly far away. It is a fast moving source, and the frequency is below 10 kilohertz, and it has a limited tonal content. And therefore it is sort of a good estimate to give you the overall A-weighted sound pressure level. But if you would like to do a detailed study of frequency content and for hovering conditions, I mean for a drone that is in a hovering condition, this might lead to considerable errors due to this reflected wave that you will see here on the picture. And the mathematics behind here, it is of course, if you are in a hovering situation, you are just above the microphone, you will have a reflection and you will have a direct wave. So when the reflection is 180 degrees phase shifted from the direct wave, you will have a cancellation of the noise. And there you will see if you have a hovering object and it is sending out a pink noise source directly over, you will see here that in some cases you have the signal and the signal is 94 dB. There, in some cases, you will actually measure 100 dB because you have a doubling. That means that you are actually getting a 100% reflection, and the microphone will consider to have two signals of 94 dB, which means a pressure doubling, which means a 6 dB plus, which means 100 decibel. So that will happen in some frequencies. But if you have this hovering object over the microphone, you will see other frequencies where you will see a dip, where you have a total 180 degrees phase shift, which means that you will have a cancellation of the noise because you have different phases, same frequency on the membrane of the microphone, and therefore you will have a reduction in noise measured. So that means that you will get a picture like this if you're putting a hovering object with pink noise just over the microphone, and you will see that the reflection is actually influencing the result of your measurements. So this is not good if you're having a non-stationary or a stationary noise source. Then you might say that, well, this is not an issue because I'm measuring over very soft ground, which means that you will have a lot of dampening of the reflective wave. We have also been doing a lot of simulations on this issue, and we have been simulating different ground conditions. So we have one condition here called the soft forest ground, which is 30 kilopascal, and a hard reflecting ground. So it is different impedance on the ground. And we were doing a simulation of what would be the result on the membrane. Is it so that the reflective wave is dampened on the soft forest ground? And the result when we were using the COMSOL calculation software it is that even with a very soft ground, you will have the same effect. You will have some reduction of the effect, but still it is a big difference between the different frequencies. So you will have this effect even on soft ground. So therefore, it is not a good argument saying that, well, I'm measuring in a GRAS area and therefore I don't have any reflections and therefore I don't need to do anything special here. This is an issue, and it is an issue even if you're measuring on a parking lot on top of a house or a soft forest ground. So therefore, if you're using this method for measuring a drone or an eVTOL, there will be some problems. There will be some reflections. That is an issue. And therefore, you can't really use this method for doing that. And the people writing the standards in ICAO, they were also well aware of this. So when they used this method for the subsonic jet airplanes, they said, okay, this is a source where we can actually use this 1.2 meter position, and therefore the type of noise or this noise source is actually in a shape that we can actually use this. So therefore it is a possibility, and therefore it is in the standard. The second method, this is also described in the ICAO standard. This is ICAO Annex 16, and this is for evaluation for noise certification of propeller-driven airplanes not exceeding 8,618 kilograms. And they considered this reflection issue to be an issue also on smaller aircrafts because it is closer to the noise source, the listener, and it is also more tonal content and so on. And therefore, they said the 1.2 meter is not going to work, and we would like to have a better measurement method for these aircrafts. So therefore, it was invented a new method, and this is many, many years back. And what they came up with, it is what they called an upside-down microphone. And the upside-down microphone, it is a microphone that is mounted on top of a plate. And this plate, it is a round plate, and it is a known reflection in this plate. And therefore, it should be better for this purpose. And the reason why this was introduced for this standard, it was that they already at that time, they said it's not going to work out very nicely with a 1.2 meter configuration. The theory behind this, it is that if you have a microphone mounted in a surface, you will have a double pressuring or pressure. So therefore you will get a doubling signal, and it is sort of a virtual source on the other side, and therefore you will have a pressure doubling. A pressure doubling means a plus 6 dB on the surface right here. The problem at that time when the standard was developed was that there were no traditional microphone that could be mounted on the backside of a plate, because then you had to dig a hole in the ground because of the shape of the microphone. And therefore they said, okay, in order to do that, we just need to put the microphone very close to the plate in order to have a total reflection, and there you will have a total reflection giving a pressure doubling on the membrane. So the mathematics behind it is that the height, the air gap between the microphone and the surface should be half the size of the microphone diameter. So usually we are using a 1/2-inch microphone. That means that the distance between or the diameter is 12.7 and the air gap should be half of it. That means 6.35 millimeters or roughly 7 millimeters. And therefore, when you're reading instructions or how you're going to mount it, they say half-inch microphone. They say 7 millimeters air gap between here. The only problem with this method, it is that you actually get a problem because you have a fixture. You need to keep the microphone in place here. And therefore you need to have a structure that is disturbing higher frequencies. But I will come back to that. So this one, it is a drawing of the microphone. It is a round plate. It is defined in the standard. What is the thickness of the plate? What is the diameter of the plate? What is the aircraft flight track that it should be moving in? And then it is also this air gap diaphragm about the plate, 7 millimeters. And the leg diameter for this structure here should be less than 2 millimeters. So then you might ask a question or a couple of questions here. First of all, why is it that the microphone is not placed in the middle of the plate here? Well, when they developed the standard, they were actually considering that at the first, but then during studies, they have basically said that it's better to place it on the side here, on this side here, because that is giving a less impact on the impedance on the ground around it. Because if it was in the middle, it could actually have an impedance that is affecting the microphone measurements from all sides. That is increasing the dependency of what sort of GRAS or ground conditions you're putting it out on. We have been doing some simulations on that, and we have been using the COMSOL package again, software simulation tool. And we have been putting it on the center point or done a analysis on the center point, and we have been doing it on the required position according to the standard. So you will see here, this should be a totally straight line. And you can actually see here that it is measuring better if you have the position that is the 15 centimeter radius position. So it is more flat, the red curve, than the blue curve, and the blue curve, it is the middle position. So this is turning out to be perfectly correct. It should be a little bit misaligned according to the standard, and that is correct also for simulation, but also for theoretical calculations of where the microphone should be located. The second question we had when we saw this configuration, it is what is the distance, what is that going to give for different result if we're actually changing the distance a bit? And we found out that a very small variation of the air gap between the membrane and the reflecting ground board have a significant impact on the measurements at 10 kilohertz. And that is very difficult to configure or to set up the microphone accurately after calibration or verification. You know, when you do these kinds of tests, you're going out with the microphones, you're putting it in onto the grass or a ground condition where you find it suitable. And then just before the measurement, you would like to calibrate or at least verify the functionality of the system. And therefore you're putting a calibrator on top of the microphone, which means that you have to turn it upside down or correctly, if you like, and then you have to put it back again in an upside down configuration. And by doing so, there is a risk that you actually are misaligning the distance between the membrane and the plate. So we did this simulation, and you can find here we have 3 different colors. We have 7 millimeter, that is the green curve. We have 4 millimeter distance and 9.6 millimeter distance. And you can see here, if you take the green line here, that is the most flat line up to 10 kilohertz. That is within the plus minus 1 dB. And if you take the air gap of 9.6 millimeter, there you have a much less straight line than before. And also at the air gap 4 millimeters, you have a big difference on the curve here. So therefore, it is very important that you're keeping it to 7 millimeter. A little bit of a misalignment could do a lot on the different measurements you're doing. There is also another takeaway from this picture. It is that what is actually happening over 10 kilohertz, you simply don't know. Because over 10 kilohertz, it is not useful, this measurement. It is simply not a flat curve any longer, and therefore the behavior of the microphone system over 10 kilohertz is not trustable. So this method here, it is only suitable for up to 10 kilohertz. We were also doing a little bit of another test here in our factory, we had the idea that over 10 kilohertz, there were some disturbance from the actual sort of structure in itself, because it is mounted in the sound field, and therefore the higher frequency, the more disturbance you're actually creating. And that's the reason why it was defined in the standard that the legs of this construction should be less than 2 millimeters. So we were doing some analysis on that, and the test that we were doing, we were putting a reference microphone on the backside of the plate or a surface, and then we were putting 3 different kinds of microphone. So we put a 1/8 of an inch microphone, we put a 1/4 inch microphone, and a 1/2 inch microphone. And our idea would be that if you put a 1/8 of an inch microphone on top, it would actually disturb the test less than if you were putting a 1/2 inch of a microphone, because simply it's a bigger microphone. And by doing that, we saw the different sizes, the 3 curves here. You see the 1/2 inch, it is actually deviating from a straight line at the earliest. So this one is actually disturbing a little bit before, and then over 10 kilohertz, it goes down to non-useful data. And if you take 1/4 of an inch, that's the red one, and then you have the blue one, it's a 1/8 of an inch. So the theory seems to be correct. If you have a smaller item that you're putting into the sound field, it is disturbing less, which means that it is more equal to the reference measurement. However, it is not fundamentally changing the behavior over 10 kilohertz. So even if you're putting in a 1/8 of an inch microphone, the effect is still that you can't really use it over 10 kilohertz. So therefore, this method is only useful up to 10 kilohertz. After that, you don't simply don't know what is going on. Great. So the conclusion for this ground board microphone, it is that reflection is not an issue, because you don't have this effect that you had on the first setup, where you had a reflecting wave. Here you have a pressure doubling, because you're basically having the microphone in the plate. And compared with free field measurements, the result will be almost 6 dB higher, which is a pressure doubling. The air gap of the half size of the microphone diameter is very important, and it is giving good measurements of tonal content up to 10 kilohertz, but measurements about 10 kilohertz is simply not possible because of the construction in itself. So, having said that, now we're coming to UAS, or if we talk about eVTOL. There we do have a different kind of noise. So therefore, first of all, when you're doing noise measurement for lightweight or small multi-rotor UAS, Of course, if you can be in an anechoic chamber, it's good. And there are standards that are defining that. It is almost free field conditions. So these goes for very small drones. And of course, if you're coming up to a certain size, they are too dangerous to put into an anechoic chamber. And therefore, you have to do the tests outdoor. There is no other way than being outdoor. And the outdoor environment is not providing a free field condition. So therefore, you have these ground reflections, and therefore you have to have the right microphone configuration in order to do the measurements. We have been going through 3 traditional methods, and there were pole-mounted microphones. You had 2 different configurations. You had the 6 to 10 meter configuration. That is for more fixed installations like airport noise monitoring systems. You had 1.2 for more sort of one-off measurements, where it is more simple to put it in 1.2 meter, but it is requiring a noise source that are certain criteria is fulfilled. And then in order to have this certification of propeller-driven aircrafts, the inverted microphone over reflected plane has been developed over the time and is now a part of the ICAO standard. So when the late ISO standard, the 5305, was developed, a new method had to be developed in order to cope with the challenges that I have just pointed out. So this new method, it is an integrated microphone in a reflected plane. And as I said to you in the very beginning, the distance between the noise source and the receiver is very short when it comes to these smaller drones. It could be a stationary source because it can hover. The frequency could be about 10 kilohertz, and it has a tonal content. So as you can see, the old traditional methods are not really suitable for this measurement. So yeah, this is basically what I was putting up as issues. So it's not really possible to use the existing methods for doing this. And therefore, we have been developing a ground board that is doing measurements with a flush-mounted microphone. So what we have done, we have taken the best from the standard. We have taken this plate, exactly the same configuration. And then instead of putting an upside down microphone, because that was the only possibility some 20, 30 years back, and we have basically integrated a small microphone inside the plate. So now we don't have any disturbing structure on top of the plate. We just follow the standardization rules of having this plate. We have exactly the same geometry of this plate, exactly the same size of it, and the thickness of it. The only difference that we have introduced, it is that we have put in a flat microphone, a half-inch microphone, in the exact same position. And this is tailored for the precise eVTOL noise measurements. And this is supporting the broadband and tonal noise analysis. So I will show you here that this configuration here has no interface from reflections. So there's no reflecting signals from the ground because it is integrated in the ground. It is suitable for measurement of tonal content. It has a flat frequency response from the lowest frequency to the highest frequency. It is not having any cutoff at 10 kilohertz because we don't have any structure on the top here. And it is no moving parts or fixtures. It is small size. It is easy to transport and install. And the reason how this is actually possible, it is that we have made a new type of microphone that can be integrated into a plate like this. So the challenge 25, 30 years back was that it was a pencil-like microphone that required to dig a hole in the ground in order to put it on the ground. Now we have made a flat microphone, and therefore we can integrate it into the plate. And this will give you a result that is a pressure doubling, because now we have this a virtual virtual source on the other side that is doubling the value. So if you're applying a 94 dB signal, you will measure 100 dB. So it is a half-inch microphone, a pressure microphone that is integrated here. Another very positive thing it is that you can actually do in situ calibration or verification. We have adapters for this microphone, so we can put a pistophone directly on top of the sensor when it is installed in the field, or we can use a simple calibrator or a unit for verification of the signal. So we have all the adapters for doing that. So that will enable a fast and accurate calibration. So is this proven in the field? Yes, it is, of course. We have developed this one in cooperation with NASA, and NASA has been sort of acknowledging the issue that the upside down configuration, it's not really suitable for this application, and therefore recently, the last 3 or 4 years, this is the de facto standard microphone for NASA when they are doing tests and verification and working on standards for this area. So if you search on the internet for NASA and Joby Aviation, you will find one of the tests that they are doing where they are using more than 50 specialized microphones that are collecting the data. And the reason why they need to have these very accurate microphones for this purpose, it is to have a public acceptance that the measurements that they're actually doing and the data that they are publishing is 100% correct and it cannot be challenged. So a little bit of a wrap up, it is that we had this Annex 16 for larger airplanes. There, if we do that method for drones and UAVs and so on, you will find out that you have the risk of having this signal where it has reflections and it will not give you the right result. If we go for the Annex 16 for the smaller airplanes, there you have the upside down, and this one is disturbing the measurement. So it is good results up to 10 kilohertz, but about 10 kilohertz, it's not really useful because the data is simply not trustful. And then we have this new type of microphones that we have developed where it is integrated in the plate. This is now described in the ISO 5305 from 2024, and that is for measurement of UAS and smaller UAVs. And this is then giving you a flat response for 20 to 20 kilohertz, and this will give you the advantage that it is eliminating any interference from ground reflections. So all in all, this microphone is actually giving you a much better result for these kinds of measurement. So this is a little bit of the test, the Joby Aviation test, and you can read a lot more about that on the net. It's all published in papers, but also on Joby's homepage and on other NASA pages. So you can find more information there. We have been doing this, and one of the issues for these kind of concerns that the public is having, it is that several investigations of what people are afraid of, it is that safety it's emerging as the primary concern of these new systems. So more than half of the respondents have stressed that safety of the aircraft is the most important. But as the second most related issue, it is the noise related issue. almost 50% of the respondent is answering that the sound generated by these kind of aircraft is very concerning, and therefore it has to be addressed. And having some standards that can give the industry and the legislators a common ground to stand on, it is boosting the industry quite a lot, because if you know that the devices that you are manufacturing in your country can be used globally because you're using the same standard, the same way of doing measurements, it is opening up the entire market. Instead of having a situation where you have to noise certify your vehicles in all different countries. That is cumbersome, and it will add a lot of cost to your projects. So it's quite important to have these kind of standards. So the ISO 5305, we have been a part of shaping this standard by doing these works together with NASA, and we are expecting that this microphone is going to be rolled out in more of these standards, because this is the only way you can ensure that you have a reliable data and a flat response from 20 to 20 kilohertz. So we are very proud of being a part of this, and if you have any questions or if you have any comments, leave it in the chat file of this, and I'll try to come back to you directly now, or if we don't have time right now, I will respond to you later on. You are always welcome to contact me. You can find my details down here, and you can also revisit this presentation. It will be available on our homepage, where it is a webinar that you can see more than one time, or you can give it to your colleagues, or if you have any other colleagues that might be interested in it. So now I will just check whether we have any questions coming in so far. And I have one question here that is actually quite good. It is a question about this flat response, and if this microphone, the new microphone, is actually having a flat response, is that a better microphone for use in all different applications, also for the other ones that are already standardized? And the answer is basically yes, it is. It can be used for all different kinds of aircraft, fast moving, slow moving, hovering, and everything in the air, because it is not having any of the disadvantages that the old ones are having. Having said that, a standard is a standard, which means that you can't really use the new method in a certification of a jet airplane according to the GRAS standard, because that standard is already defined and it is defining another method. When it comes to the data quality, the data quality is actually going to be better with the flat microphone with an integrated microphone. So I hope that would answer that question. I will also add on a little bit. We believe that this type of measurement with an integrated microphone will be rolled out also in newer standards, because this is the most efficient way of doing the measurement if you would like to have accurate data to compare with others. So we still have possibility to put questions in. Oh, I have one more here, and it's actually a topic I haven't been talking about at all. What about environmental conditions? What about wind and so on? And it is, for this flat microphone, we have an integrated windshield. And this integrated windshield, it is a snap-on method. So you basically can take it off and you can do your calibration and then you can put it on again. And this will of course reduce some of the wind-induced noise in the microphone. So that will give you also a more or a better measurement in slightly windy conditions. So I think we will end the session now. And again, if you have any additional questions or comments, please do not be shy. Put it into the chat or write an email to our mailbox. And we will always answer all the questions or comments that we are receiving. Or you're welcome to link up on LinkedIn with myself or with our homepage. And you can always send a mail to me as well. Thank you very much for this time and hope to see you soon again in another webinar. And thank you. Bye-bye.